This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. All right, folks, let's dive into this paper. You only look once. Unified real-time object detection. It's a classic in the field, introducing YOLO, a revolutionary approach to object detection. For our expert audience, let's cut to the chase. What were the key architectural innovations that made YOLO so impactful?
The core innovation was the unification of the entire object detection pipeline into a single convolutional neural network. Previous methods, like DPM and RCNN, were multi-stage processes involving separate feature extraction, region proposal generation, classification, and bounding box regression. YOLO elegantly bypassed all that by directly regressing from image pixels to bounding box coordinates and class probabilities in one shot. This end-to-end approach allowed for direct optimization of detection performance.
That's a huge simplification. But how did they handle the spatial constraints inherent in predicting bounding boxes directly from a grid? What were the trade-offs?
They divided the input image into an SX grid. Each grid cell was responsible for predicting B bounding boxes and their associated confidence scores and class probabilities. This grid approach introduced spatial constraints. Each cell could only predict a limited number of objects, leading to difficulties with closely spaced objects or small objects. The trade-off was speed. This unified architecture was significantly faster than its predecessors.
The paper mentions a confidence score. Can you elaborate on how that was defined and used?
The confidence score was defined as the probability of an object being present in a grid cell multiplied by the intersection over union, IOU, between the predicted bounding box and the ground truth box. This provided a measure of both the object's presence and the accuracy of the predicted bounding box. At test time, this confidence score was multiplied with the class probabilities to obtain class-specific confidence scores for each box.
The paper highlights YOLO's speed. How did they achieve such high frame rates, and what hardware was used?
The single network architecture was the key to speed. Their base YOLO model processed images at 45 frames per second FPS on a Titan X GPU, while a smaller, faster version, Fast YOLO, achieved an astounding 155 FPs. This real-time performance was a major breakthrough.
The paper also discusses the loss function. What was notable about their choice, and how did they address some of its limitations?
They used a sum-squared error loss function, which is simple to optimize. However, it didn't perfectly align with maximizing average precision. They addressed this by weighting localization error more heavily than classification error and introducing weighting parameters, Dord and Mitterbejeka, to balance the influence of confidence predictions from cells with and without objects. They also predicted the square root of bounding box width and height to address the issue of unequal weighting of errors in large and small boxes.
Let's talk about the network architecture itself. What was the inspiration and what modifications were made for object detection?
The architecture was inspired by Google Net, featuring 24 convolutional layers followed by 2 fully connected layers. They used 1x1 reduction layers followed by 3x3 convolutional layers, similar to Lin et al.'s network in network. For the detection task, they added 4 more convolutional layers and 2 fully connected layers, and increased the input resolution from 2024 by 224 to 448 by 448 to capture finer details. They also pre-trained the convolutional layers on ImageNet.
The paper compares YOLO to other detection systems like DPM and RCNN. What were the key differences and advantages of YOLO in those comparisons?
YOLO's main advantage was its speed and simplicity. DPM used a sliding window approach, while RCNN and its variants used region proposals, both resulting in complex, slow pipelines. YOLO's unified architecture eliminated the need for these separate stages, leading to significantly faster processing. While YOLO had higher localization error than RCNN, It had far fewer background false positives.
The paper mentions that YOLO struggled with small objects, especially those appearing in groups. Why was that the case?
The spatial constraints imposed by the grid design limited the number of nearby objects that could be accurately predicted. Small objects clustered together often fell within the same grid cell, exceeding the cell's capacity to predict multiple bounding boxes. The relatively coarse features used for bounding box prediction also contributed to this limitation.
How did the authors address the issue of overfitting during training?
They employed dropout after the first fully connected layer to prevent co-adaptation between layers and used extensive data augmentation techniques, including random scaling and translations, and adjustments to exposure and saturation in the HSV color space.
The paper presents results on the Pascal-Voc dataset. What were the key performance metrics and how did YOLO compare to other real-time detectors?
YOLO achieved a mean average precision map of 63.4% at 45 UPs, significantly outperforming other real-time detectors at the time. Fast YOLO, with its smaller network, achieved 52.7% map at an impressive 155 UPs. These results demonstrated a significant improvement in both speed and accuracy for real-time object detection.
The error analysis compared YOLO to FastR-CNN. What were the key differences in their error profiles?
YOLO had a higher rate of localization errors, meaning it struggled to accurately pinpoint the location of objects. However, it had significantly fewer background errors, false positives, compared to FastR-CNN. This difference in error profiles suggested a potential for combining the two models to improve overall performance.
And how did combining YOLO and FastR-CNN affect the results?
Combining YOLO with FastR-CNN resulted in a significant performance boost. YOLO's ability to filter out background detections from FastR-CNN's predictions led to a 3.2% increase in MAP on the VOC 2007 test set. This demonstrated the complementary nature of the two models' strengths and weaknesses.
The paper also explores YOLO's generalizability to new domains. What were the findings?
YOLO outperformed other detectors, including DPM and RCNN, when tested on artwork datasets, Picasso and people art. This was attributed to YOLO's ability to learn generalizable representations of objects, focusing on size, shape, and spatial relationships rather than relying heavily on pixel-level details.
That's interesting. Could you elaborate on why YOLO generalized better to artwork than RCNN?
RCNN heavily relies on selective search for region proposals, which is tuned for natural images. Its classifier only sees small regions and requires good proposals. Artwork differs significantly from natural images at the pixel level, hindering RCNN's performance. YOLO, on the other hand, models object size and shape and relationships between objects, which are more consistent across domains.
The paper concludes by highlighting YOLO's suitability for real-world applications. What makes it so well suited for these applications?
Its combination of speed and accuracy makes it ideal for real-time applications like video processing and robotics. The real-time performance, coupled with its ability to generalize to various domains, makes it a robust and versatile object detector.
The paper mentions using a leaky ReLU activation function. Why was this chosen over other activation functions?
Leaky ReLU helps mitigate the vanishing gradient problem that can occur with standard ReLU, especially in deeper networks. The small, non-zero gradient for negative inputs allows for continued learning even when neurons have negative activations. This contributes to faster and more stable training.
The authors used a pre-trained model from ImageNet. What was the benefit of this approach?
Transfer learning from ImageNet provided a strong starting point for the convolutional layers. Pre-training on a large data set like ImageNet allows the network to learn general features that are useful for various tasks, including object detection. This reduces training time and improves performance, especially when the data set for the target task is relatively small.
The paper mentions using a batch size of 64. How does the choice of batch size affect training?
Batch size influences the gradient estimate used during optimization. Larger batch sizes provide a more accurate estimate of the gradient, but require more memory and computational resources. Smaller batch sizes introduce more noise in the gradient estimate, but can lead to faster convergence in some cases and may help escape local minima. The choice of 64 represents a balance between accuracy and efficiency.
Looking back, what are some of the limitations of the original YOLO architecture that have been addressed in subsequent versions?
The original YOLO's main limitations were its struggles with small objects and localization accuracy. Later versions, like YOLOF 2 and beyond, address these issues through improvements like anchor boxes, better feature extraction, and multi-scale training. These improvements significantly enhanced YOLO's performance and addressed many of the limitations discussed in the original paper.
This has been a great discussion on the seminal YOLO paper. Thanks for the detailed insights.